Audio Jungle. Audio Jungle.
So second component of turbojet engine is compressor. So number 2 is nothing but compressor. This is the second component. Okay. So as we had seen, okay. So here, if you check, so all right. Now where is the compressor? Compressor is here only. All right. So I said if I will consider A here, this is 1, this is 2, this is 3, this is 4, and this is what? 5. That numbering we had taken. So if you check, this portion is nothing but diffuser, this is the compressor, this is the combustion chamber here, this is the combustion chamber, this is the turbine, and this portion is nothing but nozzle here. That well explained, okay, that numbering and all. Right. So if you check, this is the free stream air here, it is coming. So that compressor number, if you check, it is nothing but 1 to 2. Okay, so separate this component will take. No? This is what? Compressor. This diffuser part is what done here. Okay, already first component I explained. Now second component is compressor. So this compressor I am going to take separately. So this compressor is nothing but rotatory device, right? Like diffuser was also used to convert kinetic energy into pressure rise, but it was a static device. But this compressor is what? Rotatory device. It is rotating, and obviously this compressor getting work from the turbine, so it is consuming work. Okay, so that compressor work I can say it is nothing but WC. So work, I must say, work absorbed by compressor will be WC. Now check, this station is nothing but, as I have told you, inlet of compressor will be 1. So temperature at inlet, inside the engine always you talk total quantity, stagnation or total meaning will be same. So total temperature will be T01 at inlet, because this is the station number 1 and this is station number 2. So what is the temperature here? It is T02. What is the pressure here? It is P01, and what is the pressure here? It is P02. All right, this is the way to write the numbering process and all. It is work consuming device, work absorbed by compressor or work consumed by compressor. And if I draw the TS plot, so in previous lecture I had drawn for all components I had drawn TS plot, right? TS plot I had drawn for all the components, now one by one need to draw here. Now here I will draw for the compressor. So I can take two pressure line in TS plot. This is the pressure line. I can say this is nothing but P01 total. Another pressure line will be P02. Okay. So respect to temperature, definitely it will have, but I can say this is the isentropic and this is the actual. Isentropic and actual, I explained you. Isentropic meaning is entropy must be constant. Okay, entropy must be constant. So entropy must be constant, that means it should be a straight line. Okay, it should be a straight line, like this is the straight line. It means it is the isentropic and actual will be increasing the entropy. See, entropy is what increasing here. Okay, all right. Now so if you say the temperature, so definitely with respect to this point, this will be the temperature here. Okay, this will be the temperature T0 2, but with respect to this point, this will be temperature T0 2 dash. Okay, why it is dash? T0 2 dash means isentropic temperature rise. Okay, T0 2 means actual temperature rise, and definitely here temperature will be T0 1. You can draw if you want to here for your understanding only. This is the T0 2 dash. This is the T0 2 dash. This is the T0 1. This point is what? Obviously it is 1. This is 0.2 and this is 0.1. All right, and here this will be T0 2. So there should not be any kind of confusion. T0 2 dash is called isentropic, because what is the work of compressor? To raise the pressure. Okay, and obviously pressure will rise, then temperature will rise. So isentropic temperature rise, it is called isentropic temperature rise. And what is the T0 2? It is actual temperature rise. Hope this one is very clear to you. So two things you need to remember for the second component, which is the compressor. This is what compressor here. So you know the key points for compressor. And if I'm writing key points, that means all points are important for the numerical. Okay, as well as theory also, but numerical is our main concentration. Key points for compressor. And this compressor is what? Between 1 to 2 you are talking. Okay, what is the number one point? Number one point is what? This compressor is a rotatory device. Rotatory mechanical component. And absorb or consume power and energy, which is supplied by another rotatory component, which is nothing but turbine. Okay, number one important. Number two, for this compressor also will have two important points. I mean two type of the calculation. If you do numerical, what is the calculation? One is called isentropic efficiency. Isentropic efficiency. Okay, so because isentropic efficiency and it is for compressor, so eta c if you write, that is enough. So eta c is nothing but it is also just because compressor is what to rise the pressure and temperature. So it is just like a diffuser, but difference is diffuser was a stationary device and compressor is rotatory device. That is the only difference. Otherwise both diffuser and compressor both were doing the same work. Same work in the sense for the same purpose. What is the purpose? To rise the pressure. So what was the diffuser efficiency? If you remember, isentropic efficiency was isentropic rise divided by actual rise. So I need to write, and it is also because it is isentropic efficiency, so it will be related to the temperature rise. So isentropic temperature rise divided by actual temperature rise. Okay. So one more thing I will tell, don't get confused. Sometimes in few books it will be given in terms of enthalpy. So you can say isentropic enthalpy rise divided by actual enthalpy rise. So but meaning will be same. Okay, so it is enthalpy or temperature, both are the same thing. So compressor efficiency, if you say isentropic enthalpy rise, so what is the isentropic enthalpy rise? Check again. Isentropic, see, I explained that day also, and today also I'm going to do the same thing. This T naught 2 dash and T naught 1, this is the T naught 2 dash minus T naught 1, it is the isentropic rise. Isentropic rise, and T naught 2 minus T naught 1 will be actual rise. It should be very clear. Okay, so see, this is the T naught 2 and T naught 1, correct? So here isentropic enthalpy rise, you can say, because you are writing in terms of enthalpy, so isentropic enthalpy rise means H naught 2 dash minus H naught 1 divided by actual will be H naught 2 minus H naught 1. Okay, this is the actual. But if you write in terms of this enthalpy, you can write in terms of temperature also. So what you will write, see, you can write eta C is equal to, what is the enthalpy? It is Cp H naught 2 dash, hence it is T naught 2 dash minus Cp H naught 1. So you can write Cp T naught 1 divided by H naught 2, you can write Cp T naught 2 minus Cp T naught 1. So finally what you will get, it is T naught 2 dash minus T naught 1 divided by T naught 2 minus T naught 1. Okay, this is the uh, compressor isentropic efficiency. Okay, so always remember, this is the compressor isentropic efficiency. You can write in terms of enthalpy, it's your choice, or you can write in terms of temperature. So T naught 2 dash minus T naught 1, it is T naught 2 minus T naught 1. All right, now this is the very important formula. It will be used for the numerical. Okay, it will be used for the numerical. This is the point number 2. What is the point 3? Key points. As I told you, what is the compressor? Compressor is a rotational device or mechanical device, you can say. Mechanical device, if you say, it becomes rotational device. It is a rotational device and it will consume work. So what is the work? Work absorbed by compressor And when I explained the cycle, like on which cycle all the jet engine is what based, then that time I explained the process. Compressor process was uh, it was a reversible adiabatic or isentropic compression. Yes or no? That was the process I had explained. And in isentropic compression, if you calculate the work for the compressor here, okay, so then it will be WC, which is consumed work, and check here the cycle, which is nothing but 1 to 2. See which pressure is what higher, T naught 2 is what higher than T naught 1, because you are going to write actual work, okay, you are not going to talk isentropic work and all, actual work. So what is the actual work? It will be MCP delta T, right? So if you calculate, then finally you will get MCP delta T. This is the thermodynamics relation, and you might have seen that work calculation in the heat and work chapter. So how to calculate the work and all that, you know. So what is the mass flow rate here? Mass flow rate. So mass flow rate is what? Only air. Okay, M air, Cp also air, and delta T is total temperature, which is nothing but T naught 2 minus, because I am writing actual work. So T naught 2 dash T naught 2 minus T naught 1 will be the compressor work, and this work will be absorbed by the compressor. Okay, so this is the third very important points for the compressor. I hope this one is clear to all. Right, so this is the second component. So in second component, two very important parameters you got: compressor efficiency, you know how to calculate the efficiency for the compressor, and second was work absorbed by compressor. So it is nothing but WC, which is MCP delta T. M is the mass flow rate, and till compressor there is no fuel added. So what mass flow rate you will write? M dot air, and it will be given to you Cp of air T naught 2 minus T naught 1. Okay, this is the formula. Now we'll go for the formula of the eta C for the compressor you had seen. For the compressor you had seen two things only important here. Meanwhile, what is that? One, compressor efficiency, it is nothing but T naught 2 dash minus T naught 1 divided by T naught 2 minus T naught 1. This is the isentropic efficiency. Similarly, here you can write the compressor work, which is nothing but Cp of air, okay, T naught 2 minus T naught 1. So this two point basically important. Once you solve the numerical, so this will be used. So just keep in your mind properly. Okay. Now we'll go for the third component, and third component of jet engine is the combustion chamber. So third component is nothing but combustion chamber. Or combustor. Okay, and what is the numbering for it? So see this diagram first. Here I have drawn the combustion chamber is what? Between 2 to 3. So you can say this numbering will be 2 to 3. That means combustor is what? Between 0.2 to 3, not 2 to not 3. Okay, I can consider, and even though it is almost constant, okay, combustion chamber is what? Almost constant, not exactly constant, but it can take almost constant. So I'm just going to take this. This is the combustion chamber. Okay, in the combustion chamber, what happening? So this is what CC, no? Combustion chamber. So in combustion chamber, just focus what are the points. So points are not 2 and not 3. What happening in combustion chamber? Very simple. Air will be coming from the compressor and it will be entered in combustion chamber. So what is the air? M dot A, you can say. Then what is the work of the compressor? To convert chemical energy into fuel energy, chemical energy available in fuel into thermal energy. That is the work of combustion chamber, right? So but here the fuel will be added, and what is the fuel? M dot F. M dot F is the fuel. Okay, M dot F is the fuel and it will be added here. So then what will happen after adding the fuel? It will start burning. Okay, so here the combustion will be starting. This is the, you can say, combustion started here. Okay, in combustion chamber, combustion is what is started. Then what is the mass flow rate coming outside? So that mass flow rate will be the combustion products and it will be M dot A plus M dot F. Always remember, okay, and it is called as M dot gas. The mixture of air and fuel also called as gas. Always remember, okay. So this is the things in combustion chamber. What is the work of combustion chamber? Already you know, but in short I will write: convert chemical energy in fuel to thermal energy. Okay, number one. Number two, it provide, it's a place, na, place where combustion of air plus fuel mixture, combustion of air plus fuel products occurs. Okay, all right. So what is the important point here? Two important points. Okay, combustion chamber or combustor. Two important points you will have. Okay, what is that? From combustion chamber you will only get fuel to air ratio. Fuel to air ratio. Okay, fuel to air ratio in combustion. Whenever they will ask fuel to air ratio, so fuel to air ratio. So you will apply the energy balancing across the combustor, then you will get fuel to air ratio. Okay, number one. Number two, pressure loss sometimes required. Okay, because in combustion chamber pressure loss will be there. Why there is the pressure loss? Because of the turbulence. Why there is the turbulence created in combustion chamber? To mix the fuel and air properly, because without mixing, if you inject the fuel and if proper mixing is not there, then products, combustion products, you can say it is not a perfect combustion products. Why? Because if you have injected fuel, because with velocity that air is what coming, and if there is no proper mixing, then fuel particles will be without burning itself, fuel particles will go out from the combustion chamber with the air particles. It will stick over the air particles and it will go outside, because they have not, you have not mixed properly. So you know that with the air only it will go outside without burning. So for that reason it is called residence time. Okay, so in combustion chamber, that air and fuel mixtures should have a proper, first of all it should have a proper mixing. Second, that residence time means up to what time that air and fuel particles are available in combustion chamber. Okay, that is the two factors you need to understand. So for that reason only in combustor will use one device which is used to create the turbulence. Okay, and once turbulence will be created, so turbulence, this just like laminar and turbulence flow is what, so much that what it is called, random motion of the all particles. So air and fuel particles will move in randomly, so they will mix properly. Okay, and for that reason we'll have a pressure loss also. That is the demerit, but what we can do, because we want something, then we have to lose something. So for that reason, to get proper mixing, we have to create turbulence, and due to turbulence sometimes there is the pressure loss also. Sometimes, okay, I'm saying not only because of turbulence you have pressure loss. Pressure loss reason is what another factors also available in the combustion chamber, because of that also there is the pressure losses. Okay, so that is the secondary part to discuss. I'm not going to discuss yet. The important point, two things: one, you calculate pressure loss sometimes, or in problem itself pressure loss will be given in combustor. So what is the use of it, and how to get the fuel air ratio? That is the two priority over here. So I can say pressure loss, I will explain here directly. Pressure loss is nothing but delta P, I can say. What is the pressure loss? Check the numbering. Numbering is nothing but not 3 and not 2. So what is the pressure loss? That time when I explained the cycle, uh, thermodynamic cycle, so I said it is based on Brayton cycle. So in Brayton cycle I explained heat is what added at constant pressure. Yes or no? Heat is what added. Heat is added means fuel supply, which was the combustion chamber. So that this combustion chamber is always, combustion is what occurs at constant pressure. So no doubt, not 2 and not 3, P not 2 and P not 3 almost always same, I must say. But in the problem, if they have given loss in combustion chamber, then it will not be same. So what is the loss? If P naught 2 and P naught 3 is not same, okay, then you may say there is the loss in pressure, total pressure. Otherwise, total pressure must be same. Why? Because it is happening at constant pressure only. Okay. So what is the loss of pressure? It is P naught 3 minus P naught 2. So how to calculate P naught 3? They will give the pressure loss. So P naught 3 by is equal to, uh, it will be uh, P naught 3 or P naught 2. Let me check that loss, because P naught 2 is the compressor pressure, okay, which is higher, and P naught 3 is the exit of the um, that combustion chamber. All right. So definitely, if you see there is the loss of the pressure, so P naught 2 minus P naught 3. Okay, P naught 2 minus P naught 3, that will be the pressure loss, because after that turbine and all, they will expand the flow, so pressure will be continuously decreasing. So here the pressure loss will be delta P is nothing but P naught 2 minus P naught 3. Let me correct this. P naught 2 minus P naught 3. Okay. Opposite I have written P naught 2 minus P naught 3. So P naught 2 minus P naught 3. So what will be the P naught 3? P naught 3 will be P naught 2 minus delta P loss. Okay. It will be used sometimes in the problem. Always remember. One full length jet propulsion turbojet problem will solve, then all the components will come there. Okay, now what is the fuel ratio? How to get this? For this we need to apply energy equation across the combustor. So we'll write apply energy balancing across combustor. Okay, or combustion chamber. So this is our combustion chamber. Check, this is not 2, this is not 3, and this is m dot a. Okay, This is what combustion chamber, and you are adding here m dot f. So fuel you are adding, but I'm going to talk the energy. So what will be the energy here? What is the energy of the chemical energy? I'm saying what is the chemical, what is the work of combustion chamber? To convert chemical energy into thermal energy. So what will be the chemical energy? The chemical energy will be chemical heat value, okay, which is depends on the fuel heat value. M dot f into heat value will be the chemical energy, and if you multiply by the combustion chamber efficiency also, so like that effective heat energy will be like how much portion of the supplied chemical energy will be converted into thermal energy. It depends on the combustion chamber efficiency, okay, eta cc. So I say that total amount of the chemical energy which is available to convert into thermal energy is nothing but eta c, eta cc I will write, otherwise eta c means compressor efficiency also. So eta cc into m dot f into hv, this is the chemical energy, okay. I must say this is the chemical energy available, chemical energy available to convert into thermal energy, okay. I will write, don't worry. Now, so here this is nothing but m dot a plus m dot f. Fuel will go outside. All right. Now, so what is the energy balance? So total total input is equal to output. What is the total input? Check here. The total input is nothing but m dot a thermal energy, okay, m dot a into at constant pressure, so it is cp, because it is air, so you must write cp of air into what is the temperature t naught 2, okay. So this is the thermal energy added, because in combustion chamber this thermal energy will be added here, yes or no? It is coming from the compressor, m dot a cp air into t naught 2, it is sorry. So m dot a cp air t naught 2, it is coming from the compressor. So this is the thermal energy added to the combustion chamber. All right. Plus one more energy you are adding here. What is that? It is the chemical energy. What is the chemical energy? It is eta cc m dot of the fuel, mass flow rate of the fuel into heat value is equal to what is the output. So output from the combustion chamber is the gas, which is nothing but m dot a plus m dot f. I told you this is also called as gas. In few question they will be given to you gas, so you need to understand it is m dot a plus m dot f, and now this cp will be gas, okay. And what is the thermal energy? Total thermal energy which is produced from the combustion chamber, you can say, or you can say it is supplied, or you can say that this thermal energy plus this chemical energy will develop the next level of the thermal energy, which is nothing but m dot a plus m dot f cpg gas of t naught 3. This is the very important equation, and many times in examination, if you check the question, many times question they have asked based on it, okay. This is the one final equation. This equation you should know how to write, and I explained you in very simple way, okay. So what is the eta cc? Eta cc m dot f into heat value. So this is the available,
last slide.
this is the available chemical energy, okay. Eta cc is nothing but combustion chamber efficiency, m dot f is the fuel rate, it is the heat value, okay. Or calorific value Cv. Okay, what is the m dot f? M dot f is nothing but mass flow rate of fuel. Now coming to the main equation. So what you got there? M dot A Cp of air. Okay, m dot A Cp of air into T naught 2, right? Plus eta Cc m dot F into heat value is equal to Cp of gas, sorry, m dot A plus m dot F also there. M dot A plus m dot F into Cp of gas, okay, into T naught 3. What you do? You just divide by mass flow rate of air. So what you will have? Cp of air T naught 2 plus eta Cc m dot F by m dot A, heat value, it will be m dot A by m dot A plus m dot F by m dot A. Okay, here also I can write m dot A by m dot A. Both sides you have divided by m dot A. Cp of gas into T naught 3. Okay, so what you will get? You will get Cp of air T naught 2 plus eta Cc. What is m dot F by m dot A? It is small f, which is the fuel air ratio HV 1 plus small f Cp gas, okay, plus T naught 3. If you solve this equation, okay, if you solve this equation, so what you will get? Cp of air T naught 2 plus small f eta Cc into HV is equal to open that bracket. So what you will get? Cp of Cpg of T naught 3 plus f times, check what is the f. So you can write small f, you take common, so it will be eta Cc into heat value minus Cpg of gas is equal to Cp of gas minus Cp of air. Okay, it is nothing but Cp gas T naught 3 minus Cp of air divided by eta Cc heat value minus Cp of gas T naught 3. This is what? Fuel to air ratio. Okay, this is the fuel to air ratio. Done. So this is the final fuel to air ratio for the combustion chamber. So in combustion chamber, two analysis you have to perform. One is fuel to air ratio. So this fuel to air ratio, now you have small f is equal to, you have Cp of gas T naught 3 minus Cp of air T naught 2 minus, this is nothing but eta Cc into heat value minus Cp of gas T naught 3. Okay, so two things are very important in combustion chamber, you need to remember. Now we'll go for the next component of the jet engine, and this is nothing but number 4. What is the 4 number? It is turbine. Okay, check the turbine. It is also a rotatory component. So turbine is what? It is producing work. So it's a work producing device, mechanical device. This is what turbine. Please go back and check the numbering. So I think it is 3 to 4. No? Check turbine. Turbine is 3 to 4. So this is T03, T04. Actually it's not 3 and not 4 number. Okay, I will give values here. It is T03, T04, T03 and T04. For this turbine, I will draw the TS plot for this turbine. So turbine is the expansion device. Okay, in this turbine what will happen? Pressure and temperature will fall. So that means Not 3 quantity will be higher than Not 4. So I can say this is the Not 3. And for the full scale TS plot I had drawn for the engine, so if you check, this was the Not 3 and this is Not 4. All right. So this fall is nothing but isentropic fall or ideal fall, and this is the actual fall. In actual, because there is the fall of pressure and fall of temperature in turbine, because expansion occurs. It will expand. It is a rotatory component. Okay, it is a rotatory component. It is work producing device. Okay, number 3, it will expand the flow. Okay, if it will expand the flow, then obviously fall of pressure and temperature. What is the work of it? Used to rotate compressor. These are the few points for the turbine. Okay, in short I am saying, so it will try to expand the flow. What is this number? It is Not 3, and definitely this will be not 4. Sorry. So see, this is the actual, so Not 4. This you can say this is the P03 and P04. Now this correct, because this is the pressure line, and this is the Not 3 and Not 4. This point will be Not 4 dash. Okay, dash means ideal expansion. So so see, this T03 minus T04 you can say isentropic fall, okay, and T03 minus T04 is actual fall, fall of total temperature, fall of total temperature. All right, fine. So as I have shown you this full scale TS plot already you had seen, so no need to go in very deep and detail. Only this turbine component I have shown you. There will be fall of the pressure and fall of the temperature because it is expanding the flow. And one more thing, it is a work producing device, okay, a turbine. So if it is work producing the device, so let me show you this. This is what compressor, sorry, uh, three most important point for the turbine you need to write first. Turbine, okay, what are the that it's a isentropic efficiency, it is denoted by eta T, okay. Second is the work produced by turbine, it is WT. Third is work supplied to compressor, okay. How to connect this? So we'll start from the first isentropic efficiency of turbine. Number one, this is number one, this is number two, and this is number three. So number one is what? Eta T. What is the eta T? Let me write here. Eta T is nothing but called actual fall in total enthalpy divided by isentropic fall in total enthalpy. How it will be written? What is the actual fall? I have given here actual fall. Huh? T03 minus T04. If you write in terms of enthalpies, it will be H03 by H03 minus H04 divided by what is the ideal? Ideal it is nothing but H03 minus H04 dash. Okay. So if you write, this is the first point only I am saying. Turbine efficiency, it is H03 minus H04, H03 minus H04 dash. You can write here Cp T03 minus, remember this Cp is gas, okay, because in turbine we have gas, not air. Cp T04 divided by Cp T03 minus Cp T04 dash, which is also T03 minus T04 divided by, so what is the eta T? Eta T finally you got T03 minus T04 divided by T03 minus T04 dash. This is very important. Okay, question they are asking based on this, so please make a mark for this. This is the number one important point here. Number two, we have to calculate work produced by the turbine. We have to calculate, this is the number one, which is the turbine efficiency. Number four is work produced by the turbine. Number 2 point for the turbine, number 2 is work produced. Okay, so here because it's expansion device as well, try to expand the flow, and it is producing the work also. See, this station is nothing but not 3 and this station is not 4. So what is the work W2? You can say work is nothing but if it is a specific work, depends, it is total work or a specific work. If it is a specific work, it will be divided by mass, so directly Cp into T0 you will write. If it is total work, then mass flow rate into, and what is the mass? Gas into Cp of gas into delta T. So Wt is equal to what? Into Cp of gas. What is the temperature? Which one is higher? T03 is higher than T04. So T03 minus T0. So this is the but most of time you will talk about the specific work. Okay, this is the total work. What is the specific work? It will be work per unit mass. So I will denote by small w, which is nothing but Wt, and it is now only Cp gas T03 minus T04. So many times you will use a specific work, okay, because you are writing in terms of power also. It's turbine work. So you check the unit that time, accordingly the unit you do your work. Okay, I have explained both, because in few books you will get the CPT delta T only. So why it is? Because they are writing specific work, they are not writing total. If you write total work, then mass flow rate also you have to use. Anyway, this is the second point. Now third point, this is the second point, right,
Sir,
for the turbine here. So this is the second point. Okay, coming to the third point of the turbine, what is the third point? It is work supply to the compressor. All right. Okay, this is the shaft. With the help of shaft, you have to transfer the work. This work is what produced. It is producing Wt, and it is absorbing Wc. Okay, so we'll have mechanical efficiency. Okay, it is denoted by eta m, or sometimes it is given transmission efficiency. Okay, transmission efficiency means work transfer, okay, or power transfer. So eta m is nothing but is equal to, directly I am writing compressor divided by turbine work. Means how much work this compressor is what absorb, okay, from the turbine. So how you may know, so for that reason we have mechanical efficiency, okay. So this mechanical efficiency WC is equal to eta m into WT. Okay. Now, so in this situation what you will do, sometimes you may have the all value from the turbine and you need to calculate the work of this compressor work. Some data, suppose it is given, then you can calculate data from the turbine, or some data is given in turbine, you can calculate for the compressor, okay, if mechanical efficiency is given. So how to relate it? So you know that eta m, here you eta m you have, which is nothing but compressor work WC divided by WT, turbine work and compressor work, okay. So here for the compressor work, what is that? Cp of air. What was the compressor? It was 1 to 2, A to 1 diffuser, 1 to 2 compressor. So T02 minus T01. And in turbine, Cp of gas. What is the turbine? It is nothing but T03 minus T04. By your own only you can see, if you check Cp of air, T02 minus T01, mechanical efficiency of Cp of gas, so see, this mechanical efficiency basically develop the relation between the work produced and work absorbed. So as that's the reason I told you, any value if you want to calculate in compressor, so if turbine values they have given to you, then you can get that compressor value, or if compressor value they have given to you, and if you want to calculate turbine values, so with the help of this relation it is very easy to you to get that value. Done.